right? As I said, we'll be starting electromagnetic induction. So basically what we learn in this chapter is how magnetic fields can produce electric fields, and the electric field that they produce can in turn drive charges and produce current. So how to use magnetic field to produce current, and how much magnetic field or how the magnetic field should vary in order to get a certain amount of current. Those are the things that we are going to discuss. We'll talk about how an induction stove works, how wireless charging works, okay? And in the end, as part of your syllabus, we will even talk about how a generator works, okay? And towards the end of the chapter, we'll briefly talk about something called alternating current as well. Okay, so to understand all this, to understand how magnetic field produces current and how much current a magnetic field can produce and all, you need to know this quantity called magnetic flux. Can any of you tell me the formula for magnetic flux? Like, it is similar to the formula for electric flux. So based on that, can you tell the formula?
B bar dot A bar.
B dot A. Okay. BA. Someone said BA cos theta. Fine. Fine. What is flux a measure of?
Net magnetic field lines.
Flux is a measure of number of field lines passing through a surface. Correct. And in the last chapter itself, we discussed that closed integral B dot dA, that is the total magnetic flux through a closed surface. How much will this be? What is the net magnetic flux?
0, sir.
Through a closed surface? It will
Zero,
always
sir.
be 0. Why?
Because they form closed loops, the number of field line and the rings.
Right, because magnetic field lines always form closed loops. Right. So over a closed surface, the closed integral will definitely be 0. But what if it is an open integral? How to find out magnetic flux through other surfaces? We'll discuss that first. So general formula for magnetic flux would be integral B dot dA. Okay. Don't use the formula B dot A always. Some of you said it is equal to B dot A. When is this applicable? See, basically what we are doing here is, go on. When is it
Is it
applicable?
when the magnetic field is uniform?
Magnetic field is uniform. There are some more conditions also. Anyone? Okay, we'll discuss. Not an issue. Just a moment. Let me consider a curved surface. Okay, consider this curved surface. It's some random shape, okay? And let's say over this surface, there is some magnetic field produced by, we don't know what produced the magnetic field, but let's say there is a magnetic field. So you can imagine some field lines like this. Okay, clearly I have drawn field lines in different directions. So it's a non-uniform magnetic field. Let's call the field as B. It could have different magnitudes at different points, different directions at different points. Okay, now basically flux, okay, whether it is electric flux or magnetic flux, it's the dot product between field and area vector. Okay, Now you consider a small patch of area on this surface, say somewhere here. So if you look at it separately, it kind of looks like this. Let's say this is the small orange patch that we have considered. And there's a field line, the magnetic field over that patch. Let us call it as B. Okay. Now, how do you draw area vector for a surface? Suppose the area of this patch is dA. How do you assign a direction to area?
Sir, it should be like perpendicular
Perpendicular to?
normal.
Okay, it should be
The
perpendicular
surface.
to the surface. Correct, correct. So in this case, the area vector for this small patch will be in this direction, perpendicular to the surface. So that is the dA vector. Okay, remember, the area vector of a surface is always perpendicular to the surface. Now this surface, as you see, is a curved surface, right? It's not flat. So different elements will have their area vectors pointing in different directions. Okay, you take a patch here, it may have its area vector this way. So it's possible for different elements of the surface to have area vectors in different directions. Now, through this small patch of area dA, there will be a small amount of magnetic flux. So you can write d phi, the small magnetic flux passing through that small patch is B dot dA. That's the basic definition of magnetic flux. Fine. So if you want total magnetic flux over the surface, whether it is flat or curved, you'll need to integrate the flux through each small element of the area, through each small patch of area. So if you do that integration, then the formula will be this. So basically, this is one formula which always works. Okay. Now, some of you said it is B dot A or BA cos theta. We'll discuss the conditions. One of you said the magnetic field should be uniform. See, even if magnetic field is uniform, if the surface is like this, you will not be able, I'm not saying, okay, I should not say you will not be able, but in some cases you won't be able to get one area vector for the entire surface. Okay, for example, in this case itself, let's say this was a sheet whose total area is some 20 centimeter square or 20 meter square, whatever it is. One of you tell me, can you assign a direction to the area vector of this complete sheet? Complete surface. Will you be able to assign, like just by looking at it, will you be able to assign a particular direction to its area vector?
No, sir.
It will be difficult. Okay. In some cases you can. For example, suppose it's a hemispherical surface. For hemispherical surface, if you take the area vectors of different patches, their resultant, okay, the net area vector of this surface would be this way from its center along the radius. You can assign an area vector to that. In some cases, you will be able to do, but in some cases, you may not be able to do. Okay. Someone is saying, if we take a surface integral, yeah, if Pradyun, if you take integral, you can solve. Okay. I'm just explaining when we can avoid the integral. So if you are sure of the area vector, and if you are sure that magnetic field is uniform, then this formula changes to, or the integral formula, integral B dot dA can be taken as directly B dot A. You should definitely know the direction of B and the direction of the total area vector A, then this can be done. Okay. But don't say magnetic field has to be uniform, then we can use this. Even if magnetic field is uniform, if you are not able to assign a direction to area, you won't be able to use it. Okay, fine. So this is under some conditions. So let's use this formula and derive magnetic flux through some surfaces. First, let's say there is a straight infinite wire. This is a very common situation used in many problems actually. And assume there is a rectangular surface nearby. Let's say the current passing in this wire is I. This distance, take it as A, and the length of the rectangle let it be 2A. Breadth of the rectangle is again A. Tell me, will there be any flux through that rectangular surface? Generally, you tell me, when do we say there is flux through a surface, electric flux or magnetic flux? When do we say there is flux through a surface?
Or the field lines pass through it.
Field line should pass through it, means they should go from one side of the surface to the other side, like we have shown in this diagram. Okay, so field line should cut through the surface. Then there will definitely be flux through that surface. How does a straight or what kind of field lines does a straight infinite wire produce? What kind of field lines does a straight infinite wire produce?
So, like, which field lines, electric or magnetics?
Electric, you tell, sir. I'll give you.
No, sir, actually,
Uh,
so magnetic, no? So it will be closed loop, sir.
Why will current wire produce electric field? It produces magnetic field only, no? It cannot produce electric field at all. Why will I talk about field lines? Yes, what do you say? Can current wire produce electric field?
No, sir, net charge will be zero.
Okay, yeah. What did you say? Magnetic field lines will be like?
Closed loops.
In what shape? They're always closed loops. We know
Circular.
that. Circular closed loops. Okay, fine. So since the current is flowing upward, place your thumb along the flow of current, curl your right hand fingers. The field lines created by this wire, I'll just indicate some of them, will be like this. So there will be flux passing through this rectangular surface. You need to imagine this first. Visualization is most important. Okay. This is one field line, you can say. It will create many more field lines. Okay, clearly they are cutting through that rectangular surface. So there will be magnetic flux through that rectangular surface. Derive an expression for it, all of you. Total magnetic flux through that rectangle produced by this wire. Will you use B dot A here or integral B dot dA? To find out the total flux through that rectangle.
Integral B dot D.
Why?
Sir, at each and every point as we move from A to 2A, like from point.
Yeah.
So
Distance to distance.
the field will vary, sir.
The magnetic field produced by an infinite straight wire, we know the formula for it, mu naught I divided by 2 pi x. So the field produced by the wire varies based on the distance from the wire. And different points of that rectangle Okay, like this gray one, this orange one. Different points of the rectangular surface are at different distances from the wire. So that rectangle is in a non-uniform field. And since the field is non-uniform, you'll have to use integral B dot dA. Think carefully and solve all of you. Mansa, good evening. We just started with the chapter Electromagnetic Induction, and we are talking about magnetic flux and how to calculate it. So general formula is integral B dot dA. We are applying that to calculate magnetic flux through this rectangle, which is placed near a straight infinite wire. Okay. Make it fast, all of you. Yash is saying we should consider a vertical thin rectangular strip. Yeah, that is correct. Proceed. Okay. Any answer? I got one answer, mu naught IA by 2 pi multiplied with ln2. We'll see. Listen, all of you. To calculate the total flux through this rectangular surface, we are integrating B dot dA. Basically, B dot dA is the small flux through a small patch of area. Okay. And d phi is equal to B dot dA can be used, okay, if you are sure that B is uniform at least over the element dA. Okay, so you have to visualize elements over which the magnetic field is going to be uniform or is not going to vary much. Fine. So if you consider this wire, we know the magnetic field produced by the wire varies from distance to distance from the wire, and different points of the rectangle are at different distances from it. But if you take a set of points which are equidistant from the wire, okay, a set of points of this rectangle which are equidistant from the wire, will they all be under the same amount of magnetic field or not? Anyone, what do you say? If we consider a set of points of this wire which are equidistant, set of points of this rectangle which are equidistant from the wire, will they all experience the same magnetic field or not?
Yes, sir, they will.
Definitely they will. Okay. Assume this distance is x. Now you consider a rectangular strip like this. Why did I take a rectangular strip? Because once you fix the distance x parallel to the wire, you can take any number of points. They'll all be under the same amount of magnetic field. So I'm taking all those points which are equidistant from the wire. Wire is carrying the current I. Okay. And of course, the rectangular strip will have some width dx. Within that width dx, the field strength doesn't change much. So you can assume that this rectangular element that we have taken is under uniform magnetic field. Okay, so that shaded area is what we are going to consider as dA. So we need the expression for the magnetic field that it experiences or which it is under, and we need the expression for its area as well. So you can write d phi, the magnetic flux through that rectangular strip, is B, the magnetic field over it, multiplied with its area vector, dot product. Okay. Now magnetic field magnitude we know is mu naught I by 2 pi x. That's the magnetic field produced by the wire at a distance x from it. Okay. Area for now, let's keep it as dA. And then we need the angle between them. Tell me, in which direction is the magnetic field experienced by that strip? At any point on that rectangle. Into the screen, correct. Current is flowing upward. So just place your thumb in the upward direction and make your fingers point towards that rectangular strip. The palm will be facing inwards. So the magnetic field is into the screen. Okay. What about area vector of that rectangular strip? Is it also perpendicular to the screen or not?
Yes.
It will definitely be. The rectangular area, the complete rectangle is in the plane of your screen. Then area vector of any element will be perpendicular to your screen. So magnetic field is perpendicular to the screen. Area vector of every strip is also perpendicular to the screen. So the angle between them can be taken as 0. Right. So to get the total flux, we need to integrate this term. Mu naught is constant. I is the current producing the field. 2 pi is constant. But the distance x varies from element to element. The blue element is at one distance. You can take another rectangular element here. It will be at a different distance from the wire. If distance is different, the field will also be significantly different. Okay. So you need to integrate dA divided by x. Can you directly integrate dA by x?
No.
No. Because x is a variable here, then integration should be in terms of x. So you should have a dx term. So now the problem is to express this area in terms of the width dx. Now the element we have taken is a rectangle. Its width is dx. How much is the length? That was given in the problem. In problem it was given as a. Okay, that's the length. Therefore dA can be written as small a dx. Area of the rectangle, length of the rectangle multiplied with its width. Okay, if you substitute dA as small a dx, then small a goes out of the integral. Dx by x can be integrated. And to cover the entire rectangular strip, not rectangular strip, to cover the entire rectangular sheet or surface, x should vary from a to 3a. The final value of x is 3a. Side of the rectangle itself is 2a. So here it is a and here it is 3a x value. So limits will be from a to 3a. That's all. Therefore, the total flux through that rectangle becomes mu naught I by 2 pi. Okay, mu naught I a by 2 pi. Integral dx by x will be ln x. And in that you substitute limits a to 3a. You'll get ln 3a minus ln a. And log a minus log b is log of a by b. Effectively, it becomes ln 3. So the answer is mu naught I a by 2 pi ln 3. Any doubts in this? Anyone?
Then will this derivation come for CBSE board exam or something? Okay, sir.
It could. Okay. So basically understand how we are approaching problems where we have to calculate the flux. Yes, just a minute. We first visualize the magnetic field lines, because if you know how the field lines are aligned to the surface, then you'll get a rough idea whether the flux is going to be positive, negative, zero, some idea you will get. Okay. So visualize the field lines first. Then to calculate the total flux, like depending on the field, you have two different formulas, right? B dot A, one direct formula, integral B dot dA. So check whether the field is uniform or non-uniform. First visualize the field, then check whether the field is uniform or non-uniform. If it is non-uniform, proceed this way. You need to carefully choose an element over which the field can be assumed to be uniform. Okay, and then write the expression for flux on that. Through that element, integrate. Yes, what is your doubt?
Sir, can you scroll down the formulas?
Roll down.
Yes, sir. This one, like
Huh.
5L. So what will be the dimension of this? Same as B into A, right?
Of course, flux has to be magnetic field into area.
In denominator, we don't have any length, right?
You don't have. So what is A here?
So area, sir.
A is not area. A is the side of the rectangle. A is a length. Small a is a length. Yes or no?
Oh, you were saying about small a, right?
Small a is a length. Did you get it or not?
Got it, sir. Yeah, now I got it.
This part is magnetic field with proper dimensions. This part is area. And after that, we didn't change anything. We just sent the x inside. It's still here. And area was written as length A multiplied with another distance dx. Okay. A is a length, dx is a distance. So dimensionally, everything is fine. Okay. Now that you reminded of it, derive the dimensional formula and SI unit of magnetic flux, all of you. Directly tell me the SI unit, field multiplied with area. What will it be?
Tesla meter square.
Tesla meter square, TM square. Derive its dimensions quickly. What is the dimensional formula? I got one answer as m a power minus 1 t power minus 2 L square. We'll see. I don't remember dimensions of Tesla, but whenever needed, we can use F is equal to QVB. So magnetic field is F divided by QV. And we need magnetic field multiplied with area. Let us do that also. That's all. Force is ml t power minus 2. Area is L square. Charge is current into time. V is the speed L t power minus 1. So these will get cancelled. L will get cancelled. The dimensions will be m a to the power of minus 1 L square t power minus 2. Just try to recollect any convenient formula which can easily help you derive the dimensions of that unknown term. Not just in this problem, in any problem. Okay. Tesla meter square is called Weber, named after a scientist. So the SI unit of magnetic flux is Weber, which is same as Tesla meter square. Right. Now solve one other question. Let's say there is a magnetic field this way. Calculate the magnetic flux through a square of side, let's say 4 meters, lying in the YZ plane. I got one answer as 32 Weber, one answer as 0. We'll see. Can one of you tell me, when will flux through a surface be 0, even when there is a magnetic field? Field is there, but flux through the surface is 0. When is that possible?
When the magnetic field lines are perpendicular to the area.
Perpendicular to the area vector. Yeah, that is correct. Or you could say parallel to the surface. That's one possibility. Now this magnetic field here, 2i cap plus 4j cap, it's clearly a uniform magnetic field. It doesn't vary with distance or x coordinate or y coordinate, anything. It's a uniform magnetic field. So the field will be in the same direction everywhere. In such cases, flux can be 0 only if the field lines are parallel to the surface, or as Shashank was saying, Shashank or Rishi, perpendicular to the area vector is also correct. Okay. Now the field has an x component and a y component, so field lines are parallel to the xy plane. But the square is in the YZ plane, so I don't think the field lines will be parallel to this square surface. So flux cannot be 0 in this case. And because it's a uniform magnetic field and the surface is a square, things become very easy. Pradyun, what is your answer? Okay, one of you quickly tell me the formula to calculate flux when field is uniform and the surface is flat.
B dot A, sir.
You can directly use B dot A. Okay. B vector we know as it is 2i cap plus 4j cap. It's in SI units. Unit conversion is also not needed. Dot. area should be written as a vector now. The square is in the YZ plane. What is the direction of its area vector then? Okay, Pradyun, you are saying 24. We'll see. Square side is 4 meters. We can calculate its area, but what is the direction of its area? Sashank.
The direction will be perpendicular to the YZ.
Perpendicular to YZ plane means parallel to the x-axis. Right? So area of the square is parallel to the x-axis. If side is 4 meters, we know area is going to be 16 meters square. So you can write the area vector as 16 I cap. It could be minus I cap also. We just want the magnitude of flux. So plus I cap, minus I cap, we are not bothering as of now. It is 16 I cap meter square. That's all. Now you take dot product. How do you take dot product of two vectors written in analytical form or mathematical form? Multiply their x components plus multiply the y components plus multiply the z component. Ax bx plus ay by plus az bz. So 2 into 16 becomes 32. Y components, if you multiply, it will become 0. The answer is 32 Weber. Right, right. If any of you have any doubts, you can ask, because I am surprised. I thought all of you will give the answer immediately, but not many have given. Any confusion in this?
So can you
And what
can you draw a diagram to visualize? I'm not able.
Okay, I'll try. The field is parallel to the xy plane. It has an x component and a y component. And the square is in the yz plane. Just a moment. Let me download xyz planes. Okay. One second. Right. The field lines are in the xy plane or parallel to the xy plane, I should say. So it's kind of like, okay, let's assume, wait, 2 I cap plus 4j cap, no, 2 I cap plus 4j cap. The field is effectively in this direction. If we imagine the screen as the xy plane, it's in this direction. So the field lines would be like this, uniform field. And not just on the y-axis, in fact, they'll be here also, everywhere. Okay. The field lines will be like this, everywhere in space. And the square that we have taken is in the YZ plane. So you can visualize the square to be anywhere in the YZ plane. I'll put it here, 4 by 4, okay. So it's like this. Its area vector would be parallel to the x-axis. Okay. The square is lying in the YZ plane. Its area vector would be parallel to the x-axis. Is it clear?
Yes.
Right. Okay. Fine. I'll send you a worksheet based on magnetic flux calculations, uniform fields, non-uniform fields. You should be able to do it. Okay. And you will be able to do, not an issue. Now, why are we talking about flux? The chapter is about how a magnetic field can produce a current. Okay. So depending on what happens to magnetic flux, you can tell how much current will be produced or how current will be produced and all. So it's all based on the variation of magnetic flux. That's why we discussed about flux. Okay. Let us talk about Faraday's experiment. Can one of you tell me what Faraday found out, if you have I mean, if you are aware of it.
The induced EMF in a circuit is the magnitude is equal to the change in flux.
Okay, you are telling the law. Fine, not an issue. Right. So consider a coil like this. It could have any number of turns. Conducting coil can simply connected to a galvanometer. There is no source of EMF. There is no cell or anything connected. Then tell me, will there be current in this coil? If you simply connect a wire to a galvanometer, will it show any deflection? Yes or
No,
no?
sir.
No. Okay. So yeah, that is what was observed. But then Faraday, what he did, he considered a magnet nearby. Assume this is a bar magnet. Magnet will produce a magnetic field, and we know magnet behaves as a dipole. Okay. So what Faraday did is he arranged the magnet such that the axis of the magnet or the axis of the magnetic dipole coincides with that of the coil. Okay, he made them coaxial, the dipole and the coil. Okay, now we took north pole to the left. If the north pole is to the left, then you will see field lines. There will be field lines going out of the north pole of the bar magnet. So, and it's a non-uniform field, we all know that. So some of those field lines will be passing through this coil. Of course, there will be many which don't pass through the coil also. Okay, that's the field produced by the bar magnet. What Faraday observed was when the bar magnet is brought closer to the coil. Okay, when the bar magnet is moved closer to the coil, the galvanometer was found to show some deflection. Okay, there was current produced in the coil. Okay, and the needle deflected in a particular direction. And he also observed that when it is moved the other way, okay, when it is moved away from the coil, then also there was deflection in the galvanometer and it was in the opposite direction. Okay, suppose in first case the current was positive, then when the coil, when the magnet is moved the other way, taken away from the coil, again the current was non-zero and this time it was negative. The direction of current changed. Okay, then he did the reverse. What is the reverse? He kept the magnet stationary and moved the coil towards it and away from it and noted the observations. Then also something similar was observed. There was current produced in the coil. Galvanometer shows some deflection, and when coil is brought closer to the magnet, the galvanometer deflects in one direction. When it is taken away from the magnet, it deflects in a different direction, opposite direction. Okay, so then naturally he thought like, what could be causing this current? Basically, what happens when we bring the magnet closer to the coil or the coil closer to the magnet or take it away from it? As you can see, there are some field lines passing through the coil. If there are field lines passing through the coil, there will be some magnetic flux created in it. Obviously, what is the area that we are talking about? The area we are talking about is the cross section of that coil. This one, this circular cross section. Through that cross section, there are field lines passing. Okay. And because field lines are passing through that cross section, we say there is flux through it. One of you tell me, when the bar magnet is brought closer to the coil, what happens to the field inside the coil? Does it become stronger, weaker, or does it remain the same if the magnet is brought closer?
Stronger.
Strong.
Sir.
Okay. One of you quickly tell me, what is the expression for magnetic field on the axis of a dipole? The formula is analogous to electric field on the axis of electric dipole. Okay. So on that basis, at least.
D mu naught M by 4 pi x p.
What did you say?
2 mu naught M by 4 pi.
Huh. 2k p by x cube. K is 1 by 4 pi epsilon naught. In magnetism, you get mu naught by 4 pi in place of k. So 2k. P is electric dipole moment. Here you get magnetic dipole moment divided by x cube. So you can see the axial field is inversely proportional to x cube. As the distance decreases, means when the magnet is brought closer to the coil or coil is brought closer to the magnet, the field strength increases. Okay. And if field strength is increasing, we are not disturbing the area of the coil. Coil is kept as it is. We are not changing the alignment also. Okay. Keeping the axis same, we are simply bringing the coil close to the magnet and taking it away. Okay, that's what Faraday did. Okay. So area is not disturbed, field is changed. And if field changes, then the magnetic flux through the coil varies. And Faraday concluded that this is what is producing the current. Okay, he verified it thoroughly and concluded that this is what produces current in the coil. Okay. Is this clear to all of you? So basically what experiment he did and what he concluded from it. And remember this result of the result of this experiment. If magnetic flux through a coil varies, it can produce a current in the coil. Okay. How that current is produced, we will discuss in this chapter itself, but it can result in a current. And I'm using the word can. Fine. Anyway, you'll understand why I am saying can produce, not will produce. It depends on some other factors like net magnetic flux and all you'll have to see. Okay. And then he repeated those experiments by like changing the variables and all. Finally, he concluded or he came up with a law. See, to drive current, an electric field should be set up, right? Basically, an EMF is needed to drive current in a coil. Okay. So a varying magnetic flux generates an EMF. That is what he concluded. And he said that the EMF induced in a loop or in a coil when the magnetic flux varies is proportional to the rate of change of magnetic flux through the coil. E is proportional to d phi by dt. Okay. So faster the rate of change of flux, whether it is increasing or decreasing, faster it happens, greater the induced EMF. Fine. And what if flux is constant? Like you keep the magnet at a fixed distance from the coil, it will be observed that the galvanometer does not show any deflection. If the distance is fixed, the field in the coil will become constant. Okay. Of course, it could vary from point to point, but at a particular point, it doesn't change if the magnet is not moved and the coil is also not moved. So if flux remains constant, then you won't see an EMF getting induced. If flux varies, there will be an EMF induced, is what Faraday concluded. And induced EMF is proportional to the rate of change of magnetic flux with respect to time.
So faster the rate of change of flux, what happens? The more EMF.
Stronger or greater the EMF induced. Yes.
Oh. So it depends on time, right?
You should not
No.
say like that depends on the problem actually, whether it depends on time or not. It depends on how quickly the flux is changing.
Oh, okay, sir.
So isn't it E induced equals d phi by dt?
We'll come to that. From the experiments, he observed that it was proportional. Okay. Tell me, what are the dimensions of, first tell me what is the dimensional formula for EMF or voltage? Derive it quickly, all of you. Dimensional formula for voltage. Which formula will you use to derive dimensions of voltage or EMF?
F equals QVB.
F equal to
No, sir,
QVB doesn't have voltage.
So it is
Anyone? Which formula can be used to quickly derive the dimensional formula for EMF or voltage?
Current into rho L by
You know resistivity dimensions.
those.
That will make it even more complicated. In my opinion, direct definition is the easiest to use. Can one of you define potential? EMF, voltage, potential, they are all the same dimensionally. Define potential.
U by Q, sir. Like
Potential
per
energy.
unit charge.
Potential energy per unit charge. I got one answer as negative of work done by electrostatic force per unit charge. Yeah, work done by charge also you can write, or potential energy per unit charge. And Pradyum, the way you are saying it, work done or negative of work done, that is the definition for change in potential. Okay, I just asked what is potential. Okay. So energy or work, force multiplied with displacement will be ml square t power minus 2 divided by charge is current into time. So the dimensions on the left hand side, m l square t power minus 3 a power minus 1. Right hand side, magnetic flux. In today's class itself we derived m a power minus 1 l square t power minus 2. Okay, m a power minus 1 L square t power minus 2 divided by dt is time. So t, and the dimensions on the right hand side become m L square t power minus 3 a power minus 1. We see that EMF and rate of change of magnetic flux have the same dimensions. Okay. So in order to remove that proportionality, we like Faraday, all Faraday had to do was find out the proportionality constant, and he found that it is equal to 1. Okay. So induced EMF we can say is d phi b by dt, rate of change of magnetic flux through the coil. I'll put a star here because many times you see the formula being written as E is equal to minus d phi by dt. You'll understand why or from where the minus sign comes. Okay, but mostly we'll be concerned with the magnitude itself. So we are going to use it this way, d phi by dt, without the minus sign. Okay. So just remember this point. If magnetic flux through a coil changes, there will be an EMF, or there can be an EMF induced in it. Fine. Next, there was another scientist, Lenz, who kind of performed these experiments over and over, and he discovered something else. What he found was, like, he worked on the direction of current flow. When there is relative motion between the magnet and the coil, there is EMF induced, there is current flowing. Okay, and Faraday found that when magnet is brought closer, means when the flux becomes stronger, current flows in one direction, and when magnet is taken away from the coil, when the flux becomes weaker, current flows in the opposite direction. Okay, so Lenz performed further experiments and found out how to determine the direction of flow of current, or the direction in which the EMF gets induced. Okay, and what he said was induced EMF okay, that is the EMF generated by the changing magnetic flux. Fine. Induced EMF gets generated, or okay, not necessary. Induced EMF tries to oppose the change in magnetic flux through the coil. Very, very important statement. Remember this, it opposes the, or it tries to oppose the change in magnetic flux through the coil. Now, how can EMF oppose the change in magnetic flux? Let us discuss that point first. Magnetic flux is produced by the external magnetic field. Let's consider this coil and magnet itself. The bar magnet is producing magnetic flux in the coil. Okay. As a result, if that flux varies, a current gets produced in that coil. Okay, current gets generated in that coil. Now you all tell me, what does a current carrying coil behave like?
A dipole.
Dipole. It creates its own magnetic field, right? The magnet's magnetic field is there already. Now if that flux varies, the coil will have a current flowing in it, which will create another magnetic field. That's the magnetic field of the coil, not that of the bar magnet. Okay, so the current flowing in the coil creates a magnetic field, and that magnetic field is what opposes the change in original flux. Original flux is from the bar magnet. Okay, as a result of the change in original flux, that is when the bar magnet is brought closer or taken away, a current gets induced in this coil, an EMF gets induced, current gets induced. That current in turn produces another magnetic field. Let's assume current is flowing in the upward direction. The part of the coil which is out of your screen, current is flowing upward. So you all tell me, in which direction does the coil produce the magnetic field now, if current is flowing up? The part of the coil which is out of your screen has current flowing in the upward direction. So what is the direction of field produced by this coil? It's like a solenoid. What is the direction of field produced in this solenoid?
Towards left.
Towards left. You just have to curl your right hand fingers along the flow of current. Okay, it will be towards left. Correct. So this coil produces a magnetic field like this. I would like to call this as secondary flux. Okay. First one you can call original or primary. As a result, there is flux produced in the coil. Okay, due to this flux, the orange lines are arising, or that orange field is arising due to the coil's own current. Okay. So let's call it as secondary flux. Now, the direction of that secondary flux or the direction of that field depends on how the current is flowing in that coil. And when you bring the magnet close to the coil, current flows in one direction. So secondary flux will get generated in one direction. When you take the magnet away from the coil, current flows in the reverse direction. The secondary flux will be produced in the opposite direction, or the secondary field will be produced in the opposite direction. So by means of this secondary field, the induced EMF can oppose the change in flux. Okay, so basically oppose the change in flux means it produces its own magnetic field, which can oppose the change in the flux caused by the original magnetic field. So how is induced EMF opposing the change in magnetic flux? It produces its own magnetic field. By means of that, it can oppose. Let us discuss what exactly it means by opposing. Let's consider a loop like this. Simple circular loop. Assume there is a magnetic field. This is the original magnetic field, okay, produced by some other agent, not by the loop. So this is the external magnetic field. This is not the loop's magnetic field. Okay. Now tell me, if the loop is in the plane of your screen and magnetic field lines are into the screen, is there flux through this loop or not? There is flux through this loop. In which direction are the field lines passing through this loop?
Into
Into the screen, into the loop, correct. Suppose this field is getting stronger. If the field gets stronger, the flux will also get stronger, it will increase. We are not changing the area of the coil, area of the loop. We are not changing the angle between them. So A is not changed, theta is not changed. B is increasing, then flux will increase. Okay. So flux, what flux is this? Primary flux. Original flux increases. And it is increasing into the screen. Okay. Now this is a circular coil. Flux is changing. EMF will be induced. Current will flow. There are two possible directions in which current could flow. One is clockwise. The other obviously is anti-clockwise. Let us discuss both cases. If current flows clockwise in this coil, in this loop, what is the direction of its own magnetic field at points inside the loop?
Into the screen.
Others, do you agree with it or not? If current is flowing clockwise, Manasa, what do you say? What is the direction of magnetic field produced by this loop here?
So inwards.
Inwards into the screen, correct. So if the current flows this way, I'm not telling you it will flow this way. If it flows this way, it will produce secondary flux into the screen. Okay. Now primary flux was already into the screen, and what was happening to it? It was increasing. It was becoming stronger. If the secondary flux is also into the screen, will it make the net flux even stronger or weaker than the primary?
Even stronger, sir.
Obviously, the fields will get added, flux will become much higher. Okay. The primary flux is already changing. It is into the loop and it is becoming stronger and stronger, getting stronger and stronger. If the current produces a magnetic field also into the loop, then it will further increase the flux. Means it's like, it's not opposing the change in primary flux, it is supporting it. Primary flux is becoming stronger, this is making it even stronger. Okay. This is not what is observed. The current flow will not be in this direction, because if it is in this direction, it's kind of supporting the change in primary flux. Now there is another choice also. Now current could flow in the opposite direction, right? If current flows in the opposite direction, this way, then clearly the magnetic field produced by this current, which is the secondary field or the secondary flux, would be out of the screen. If it's out of the screen, it is opposing the primary flux. It's trying to make the external field weaker. Okay. And primary flux was into the screen and it was getting stronger. That second point is more important. Whether the flux is getting stronger or weaker, okay, is more important. The primary flux was into the screen and it was getting stronger. That is the change. And the induced current or induced EMF has to oppose that. So as a result, it will produce a magnetic field. Not as a result, it is found to produce a magnetic field out of the screen, out of the loop, such that it can oppose the flux which is increasing into the loop. So that will be the proper direction of current flow in this case. So to get the proper direction of current flow, what you need to see is, first, in which direction. See, flux is not a vector quantity. I should not say flux has a particular direction. Field lines have direction, but just for convenience, I'm assigning a direction to flux also. I'm saying flux is in the same direction as field lines. Okay, flux is not a vector quantity. It doesn't have a direction, but field lines have direction. So when I say flux direction, I'm talking about the field line direction. So the first thing you need to see is in which direction is the primary flux. Next, is it getting stronger or weaker? Based on that, you can tell in which direction the current should flow in the loop. Okay, let's consider another situation. The induced EMF is always found to oppose or try to oppose the change in flux. So keep that point in mind. Now, suppose same loop again, magnetic field is into the screen itself, but this time, let's say the magnetic field is getting weaker. what will the direction of current be in this case? Induced current in the loop. Think carefully and answer. Type your answers in chat. Whether the induced current will be clockwise or anti-clockwise is what I want to know. The external field is into the screen, but it's getting weaker. So what will be the direction of induced current in the loop?
Sir, I had it down.
Yeah, tell me.
Sir, how do you recognize what is primary flux and what is secondary flux?
See, secondary flux is the flux generated by the coil itself. So
And primary flux is generated by?
something else, an external agent.
Oh, okay, sir. Okay, sir.
And see, this primary flux, secondary flux, these are not scientific terms. These are just some terms that I am using to differentiate between flux produced by external field and flux produced by the coil itself. So don't use those terms in your final exams and all. They're not recognized.
Yes, sir. I was just asking to know what
No,
you
I'm
were
telling this
referring
to everyone in general. Others, I got only 2 answers, both clockwise. Others are not able to decide how the current flows. See, there are 2 choices. If current flows clockwise, then the secondary flux will be into the screen. If current flows anti-clockwise, the secondary flux will be out of the screen. You have to think on that basis. The secondary flux has to oppose the change in primary flux. So once you get the direction of secondary flux, whether it is this or this, then you can tell the direction of current induced, whether it is clockwise or anti-clockwise. Okay. To get the direction of secondary flux, we should know what is happening to the primary flux. So as I said, first thing you need to think about is in which direction is the primary flux. It's obvious in this question, crosses indicate primary flux is into the screen. Okay, so let us write that. It is inwards. And the next thing you need to think of is it getting stronger or weaker? It was given to you in the problem directly that it is getting weaker, inwards and decreasing. Okay, this is the change actually. And Lenz found out that the induced EMF opposes the change in the primary flux. Okay, so primary flux is inwards, but it is decreasing. What should the induced EMF do? Should it support the primary flux or should it decrease it further by opposing it? We need to oppose, we have to think of a way to oppose the change. The change happening with the primary is that it is decreasing. So should the induced flux, that's the secondary flux, be in the same direction as primary and support it and help it increase? Or should it be in a direction opposite to the primary and decrease it further? We have to oppose this decreasing flux. So should we create additional flux in the same direction or should we create additional flux in the opposite direction? Okay, you all tell me, what does it mean by opposing a decrease?
Opposing a decrease means increase.
Opposing a decrease means you have to try to increase it, correct? Okay, so that's the main thing here. So the secondary flux should try to increase the primary flux. Now the flux is inwards, primary flux is inwards. Inwards it is decreasing. So the secondary flux should be inwards and increasing. That's all. Okay. It can be outwards decreasing also. Let's not confuse. It has to oppose one of these. Okay. It can either oppose the inward direction and keep decreasing, or it can oppose the decreasing factor and stay inwards. If you oppose both, then effectively you'll be supporting the change. That doesn't count. Okay. So in this case, what should happen is the induced EMF should create secondary flux, which is inwards, but it is increasing. The actual flux is decreasing, so it has to increase it. Now tell me, which of those currents, clockwise or anti-clockwise, can produce an inward flux?
Clockwise.
Clockwise current, correct. So I should say secondary flux should try to support the external field. To support the external field. External field is into the screen. So the secondary flux also should be into the screen, which means current must be clockwise in this case. So based on what is happening to the primary flux, you can tell what should happen to the secondary flux. Based on that, you can tell how the current should be flowing, clockwise or anti-clockwise. Okay, let's try some more questions based on this. Just quickly tell me the direction of current. Type your answers in chat. Direction of induced current. Fine, let's take an outward magnetic field, no, not inward. And okay, the loop doesn't have to be circular, it could be in any shape. Let's say there's a magnetic field out of the screen this time. First case, the strength of the external field increases. Then how will the current flow? Second case, strength of the external field decreases. How will the current flow? Type both answers together in chat. I got one answer as A clockwise. So obviously your answer for B will be anti-clockwise. We'll see. I got another answer for A as anti-clockwise, B as clockwise. That was changed later. Okay. Others also think carefully and give your answer quickly. Okay. Let us discuss. Rishi, you tell me, in which direction is the primary flux?
Primary flux is outward, sir.
It is outward. Okay. In the first case, it is becoming stronger. Okay, field strength is increasing, so the flux will increase. Outward flux is increasing. What should the induced EMF do? Should it also produce flux outwards, or should it produce flux inwards?
I'm not sure.
What is Lenz's law?
Sir, it has to oppose change
Oppose
in
the
magnetic flux.
change in flux. Correct. The flux is outward and it is getting stronger. So if you want to oppose it, will you produce additional flux outwards, or will
Decreasing.
you
It should be decreasing.
we have to make it decrease. So will you
Yeah.
produce additional flux outwards, or will you produce additional flux inwards to make it decrease?
Inwards.
Inward, correct. So the induced EMF should drive current in such a way that it produces an inward flux. So how should the current flow, clockwise or anti-clockwise?
Clockwise.
It has to generate an inward flux. So current should be flowing clockwise in the first case. If
Sir,
it
how
flows,
do you differentiate if it has to flow clockwise or anti-clockwise? I keep getting confused.
see, curl your right hand fingers clockwise. Like along this curved arrow, curl your right hand fingers. How does the thumb point?
Downward. Thumb points like outwards.
When you curl it along that orange curved arrow,
1 second. It goes inward.
that's all.
Okay. Okay.
Here, the outward flux is getting stronger. So to oppose it, we need to produce inward flux. So based on that, you can conclude that current must be flowing clockwise. Mansa, is this clear?
Yes.
Induced current will be clockwise in the first case. Then obviously it will be in the anti-clockwise sense in the second case, because second case, what is happening? The flux is outward, primary flux. Okay, it is outward, but it is becoming weaker. Field is decreasing, so flux will be decreasing. We need to oppose that. We need to oppose that change. It is becoming weaker, means we have to make it stronger. Not we, the induced EMF has to make it stronger. Or not has to also, there's nobody dictating it, but it behaves like that. It has been found. That's why it's called a law. Okay, so it has been found that induced EMF always tends to oppose the change in flux. In the second case, flux is outward, but it is becoming weaker. So induced EMF has to make it stronger. Means it has to create additional field in the outward direction itself. Okay, and to create additional field in the outward direction, the current has to flow anti-clockwise. Then the field will be, that secondary flux will also be outward, and it can try to oppose the decrease. Okay, it is supporting it, no? So it is opposing the decrease. Is this clear to all of you? Any doubts in this question?
No, sir.
Okay. So Faraday combined this, okay, this fact that induced EMF always tries to oppose the change in flux, and the mathematical form of Faraday's law is now written as induced EMF is minus d phi b by dt. The minus sign only indicates that it opposes the change in magnetic flux through the loop or through the coil. Okay, but as I said, mostly in problems, we'll need to derive the magnitude itself. The minus sign won't really matter much. Direction we can tell, which way the current is going to flow we can tell, and based on that we can solve problems. So we'll be just using d phi by dt without a minus sign. Is this clear to all of you? Okay, anyway, nothing new. So fine, we'll stop it here for today. What all did we discuss? First, we discussed how to calculate magnetic flux through a surface. I'll send you a worksheet tomorrow with questions based on this: uniform field, non-uniform field. Then Faraday's experiments and observations. Okay. He observed that if magnetic flux through a coil changes, it can produce an EMF in that coil. Okay, and he found that faster the change in magnetic flux, stronger the EMF induced. So proportional and proportionality constant was found to be 1. Then Lenz worked more on the direction of induced EMF, how it is trying to drive current in the coil. What does it always tend to do? And he concluded that induced EMF always tries to oppose the change in magnetic flux through the coil. So you should first find out, like if you want to find out the direction of induced current, you should first see what is happening with the flux through the coil. Okay. First check in which direction it is, whether it is getting stronger in that direction or weaker. If it is getting stronger, induced field will be opposite to it. If it is getting weaker, induced field will be in the same direction and supporting it. That's all. Okay, fine. Thank you all. We'll close this session here. We'll continue tomorrow. Not tomorrow. We'll continue day after tomorrow. Yeah.